Hey, so last time we managed to see that every description gives rise to a functor. And we started going down this path because we were hoping to construct free monads on certain functors. And now here we have a candidate for these functors. So this time, let's check that we can actually construct the free monad on these functors given by a description D. It's these Args things here, right? So you might remember the way we tried to do this before was that we said that we're going to construct a new thing called free m, and before this was parameterized by a functor, but now I'm going to parameterize it by a description, and then we get given an x, and we have to return another set, right? And our idea was that because this functor here has no notion of return, necessarily, we are going to freely add in a return by just asking for it. That's how you get free stuff. You ask for things. So I'm saying that there should be a return from x to free md of x. And then we also wanted to keep the original monad. So here we should go from args d of what we first thought was of x to free md of x. So this would just include the original monad like we wanted, but then we saw that actually we have to generalize this and not just take one step, but also allow multiple layers of the free m, which we do by sticking in a free md here instead. And if you just wanted the x, then we can include it with a return. So now we can have as many layers of free monad as we want, but at each stage we add in one more of the original monad. And we remember that this didn't work before, right? Because Agda complained that this was not necessarily strictly positive because we didn't know what this functor was. But this time, if I load this, then Agda is happy and it does work. So the crucial point is that this functor here, or this expression here, is now obviously strictly positive. So this definition is allowed. And that's because if we go and look at this, we see that we have these concrete definitions, we know what it is. And strictly positive means that this x, the input to the functor, that this x does not occur to the left of any function arrows, because that's what allowed us to define this bad data type, right? And here we see that in all of these cases, the x only occurs in a very first order way, actually, right? It's just immediately here, or it's in a product or something like this, whereas we wouldn't be allowed to put something like x arrow a here. We could still allow a arrow x and Agda would still be happy, but we decided to keep things simple for now, right? So we could define this. We wasn't able to define this before, so now let's see if we can extend this to a functor. So we want that for every d in desk we should get a functor from set to set. And we know what some of the pieces are already. We know that the action on objects should be free m of d. So now we also need to define an action on morphisms, right? So do that, free m map, if x and y are sets, and if, let's see, for all x and y that are set up for every d, I should be able, if I have an f from a to b, then I should be able to go from free mda to free mdb. Call this a and b now, okay. Here's my d, it's in the beginning. Okay, so you might think that we should pattern match on the d, but that wouldn't immediately tell us which one of these we are, right? So the right move is actually to pattern match on the x. That's why we are stuck now in a way. And if it's return, then I'm going to use another return, I think. Because now I need to make a b, but I have a way of turning a's into b's. So let's use that. And here, I'll probably keep the structure the same, so it's another layer. And it looks like I can just use the fact that args is a functor. That should get me to the right spot. Okay, this looks like a recursive call, right? But now if we do this, nothing is going to work anymore. Because we still have this termination error that we might remember from before. And the reason is that here we have a recursive call, but this is not applied to something which is obviously smaller than this layer X, right? It's just given as a higher order function to this Args map. And if we look at the definition of Args map, we see that it's only ever going to apply the F to a smaller thing here. This is the only place where the F is used, right? So it's fine, but it's not obviously fine, which is a problem. So what we have to do, there's a standard way to fix this problem, is to inline the definition of Args map. So instead of using the general Args map that we've defined once and for all, but we have to have this thing as a higher order argument, we can inline it and make it specific to this function. And if we do that, then we are going to apply it to something concrete and we're going to see that it's smaller. So we have to try to do that. So we take the Args map that we have. But now, first of all, I'm going to rename it like this. Okay, and secondly, I'm not going to apply this F directly. I just want it to work in this position. So here I'm not going from any X to Y. This has to be 3m of X, and this is 3m of Y. Okay, and then we have the same problem that we had before, where we are relying on these happening to be the same all the time, which is wrong. So we should take the second argument so that we can make this one vary freely from the first one. So then the only problem is here, where we said that we wanted to specialize this to be the 3m map of F of X. And we see that we can't do that because we can only refer to things that are defined before us normally, right? So this function can refer to this one, but this one can't refer to this one because it hasn't been defined yet. So we have to put this in a mutual block. So we write mutual, and then I indent everything to be in the block. Then inside this block, everything can refer to each other. So this function can now refer to this one, even though it's now defined afterwards. And this one in turn can of course refer to this one. Like that. Okay, so that's how we define it. It's a bit of a palaver because we have to basically copy paste this function, except that we specialize it to this particular f. Right? It's a bit confusing because we also have to take another f. But this is the function we are applying compared to up here. Right? That's the function we're applying. And now the termination checker is happy because this is obviously applied to a smaller x. Right? See where this x is coming from. It's coming from here, which is smaller than this. So that's fine. And now when we are proving the laws, we are going to have the same thing again. Because this was mutually defined, it also has to be mutually proven. So we just get to do that immediately. So what we need, we're going to do this by functionality. We need this. So this is free ID for every A and D. That's the one we really want. But in order to define it, well, we can start trying to do it. This is easy. Here we have layers on both sides, so we can con with a layer. But then here we really have a fact about Args map, right? Which in fact is this fact, except specialized. Rename that. In this case, it's not going to be REFL anymore. And I think maybe that's about it. Does it fit here, or do we need to specialize it? Yeah, that fits. No, it doesn't fit. So the point is that this is talking about the prime version. And this here is not the any old A, it's a free COA. Again, we need to keep these things separate. And now it fits. And here, final case, which used to be easy, now refers back to this one again. Right. Right, so because we defined this mutually, we also had to prove this mutually. And in the same way, I've already prepared the homomorphism one. Because it's exactly the same story again. Just have a mutual proof. And then here we can do next of the map compose D. Okay, so we do get a functor. Let's rejoice. But we had to do this kind of annoying copy-paste style proofs where we had to specialize Args map in order to make this partial termination checker, which then forced us to specialize all of the proofs for the specialized Args map as well. And because this was mutual, all of the other things had to be mutual as well. So it's possible to do it, it's just a little bit annoying. And you have to do something similar in one of the coursework 3. So you get some practice on that at least. But good news, we do have a functor. Hooray.